Module 7.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 7.2. How can we numerically describe quantitative data? Part 2. Just looking at the central value of a variable is not enough to fully describe the variable. We also need to talk about how spread apart the values are. Just like there are different ways to describe the center of a data set, there are different ways to describe the spread of a data set. The range of a data set is the largest value in the data set minus the smallest value of the data set. The range is a very simplistic measurement of spread. Percentiles break the data into 100 parts. The pth percentile is the value such that p% of the observations fall below that value. Quartiles split the data into 4 parts. Q1 identifies the bottom 25% of the data. Q2 is the median. Q3 identifies the top 25% of the data. And the inner quartile range is equal to Q3 minus Q1. The IQR is the preferred method of measuring spread when the median is the measure of centrality. Any number larger than Q3 plus 1.5 times the IQR, or smaller than Q1 minus 1.5 times the IQR, is considered to be an outlier. The 5-number summary of a variable is the minimum, Q1, median, Q3, and the maximum. The standard deviation and the variance tell us about the spread of the data as well. Data that is tightly packed together will have small variance, and data that is spread far apart will have large variance. The formula for the standard deviation when calculated from the sample is given in the video script. We will not calculate these values by hand, we will use software. The important thing to realize is that the standard deviation measures the typical distance from each data point to the mean of the data point, or the data set rather. The variance is equal to the standard deviation squared. So if we calculated the standard deviation, the variance is easy to get. When we calculate standard deviation from a sample, we use the symbol S. When we calculate the standard deviation from population data, we use the symbol sigma. The formula is slightly different. Note that if you're using an online calculator to calculate standard deviation, make sure to check if you're working with population data or sample data. Standard deviation is the preferred method of measuring spread when the mean is used as a measure of centrality. Example, we will look at the variable age in the ICU dataset. Since there are 200 subjects in this dataset, n is equal to 200. The 200 values of the variable are given in the video script. Range. The smallest value in the dataset is 16 and the largest is 92. Therefore, the range of the variable age is 92 minus 16 is equal to 76. Quartiles. The easiest quartile defined is Q2 since Q2 is the median. Previously, we looked at the age observations arranged from smallest to largest. We found that the median was 63. Next, to find Q1, we want to find the median of the first half of the data set when the data is arranged from smallest to largest. The middle point occurs between 46 and 47. Therefore, Q1 is equal to 46 plus 47 divided by 2, or 46.5. This tells us that 25% of the data falls below 46.5. Alternatively, we could say that 75% of the data falls above 46.5. We can do the same thing with the upper half of the data to find that Q3 is equal to 72. Summarizing, we have that Q1 is equal to 46.5, Q2 is equal to 63, and Q3 is equal to 72. The IQR is equal to 72 minus 46.5, or 25.5. The 5-number summary for this data set is given on this slide. One thing to note is that most software will calculate the median the same way. There may be some differences in the calculation of Q1 and Q3. Definition. Box plots are plots of the quartiles of the data. They can help us spot outliers. Vertical lines are drawn at Q1, Q2, and Q3 with a box formed around them. The box represents 50% of the data. Horizontal lines are drawn out from the box to the largest and smallest non-outliers. Outliers are denoted with a dot or other small symbol. Located in the video script is an additional video with an informative example of box plots and quartiles. We will look at the variable age in the ICU dataset. Since there are 200 subjects in the dataset, n is equal to 200. Previously, we found the 5-number summary and the IQR. First, we will check for outliers. As a reminder, any number larger than Q3 plus 1.5 times the IQR or smaller than Q1 minus 1.5 times the IQR is considered to be an outlier. Here, we find that those values are 110.25 and 8.25. There are no values larger than 102.5 and no values smaller than 8.25, therefore we have no outliers. One important note is that outliers should not be removed from a data set when they are present. Outliers may contain important information about the data. Here we have a box plot of the variable age in years. Notice that the line ends at the smallest data point, which is not an outlier. The left vertical line here represents Q1, the middle vertical line represents the median, and the right vertical line represents Q3. The distance between the left vertical line and the right vertical line is equal to the IQR, and the line ends at the largest data point, which is not an outlier. Recall that Quartiles split the data into 4 parts. There's no reason for us to stop at 4. We can split the data into any number of parts that we want. Some common partitions are quartiles, which split the data into 4 parts, quintiles split the data into 5 parts, deciles split the data into 10 parts, and percentiles break the data into 100 parts. For this course, the 2 most important are the quartiles and the percentiles. We've already discussed quartiles, but we'll now discuss percentiles. Percentiles of a data set divided into hundredths or 100 equal parts. The p percentile is the value of a quantitative variable which is greater than p% of the data. It ends up that the quartiles can be rewritten as percentiles. Q1 has 25% of the data below it, therefore Q1 is the 25th percentile. Q2, the same as the median, has 50% of the data below it, and therefore Q2 is the 50th percentile. Q3 has 75% of the data below it, therefore Q3 is the 75th percentile. Example, we will look at the variable age from the ICU dataset. The values of the variable age are given in the video script arranged from smallest to largest. Suppose I want to find the 20th percentile of the dataset. In other words, I need to find the data point which is greater than 20% of the data. To find the 20th percentile, we can do the following. Write the data in order, calculate how many points would be lower than 20% of the dataset, and find the data point greater than the lowest 20% of the dataset. For this example, there are 200 data points. To find out how many data points are lower than 20%, we can calculate 0.2 times 200, which is equal to 40. Below, the smallest 40 data points are shaded in blue. Looking at the table, we can see that the value of the 20th percentile for the dataset is 40. The standard deviation gives a rough estimate of the typical distance of data values from the mean. The more spread out the data is, the more variability there will be in the data. The larger the standard deviation will be. Comparing the 2 plots here, the top data set will have values that are close to one another. In other words, smaller standard deviation. The bottom will have values that are further apart. In other words, larger standard deviation. In addition to calculating the standard deviation, it's important to know the properties of the standard deviation. The standard deviation measures the spread from the mean of the data set and should be used only when the mean is the measure of centrality. Standard deviation is equal to 0 only when all observations have the same value and there is no spread. Otherwise, it will be greater than 0. The standard deviation is sensitive to outliers because the formula for the standard deviation depends on the mean, which is also sensitive to outliers. The standard deviation has the same units of measurement as the original observations. The standard deviation can help us compare values of different variables. Definition. For an observed value of a variable x, the corresponding value of the standardized variable z is often called the z-score of an observation. Z-scores are useful because they can put variables in a common scale. A negative z-score indicates that the observation is below the mean. A positive z-score indicates that an observation is above the mean. Z-score equals to 0 indicates the observation is equal to the mean. The z-score is a measure of relative standing. For instance, a z-score of 3 indicates that an observation is larger than most other observations. Example: an incoming freshman at UK took the placement exam in Spanish and mathematics. In Spanish, she scored an 82 and in math an 80. The overall results of the Spanish exam had a mean of 72 and a standard deviation of 12, while the mean of the math exam score was 68 with a standard deviation of 8. On which exam did Julie do better compared to other freshmen? Notice that the two exams have different means and standard deviation. The student scored higher on the Spanish exam, but we need to account for the math exam being a harder exam. We can do this by comparing z-scores. The z-score for the Spanish exam is calculated as follows and equals 1.2, where the z-score for the math exam is calculated as follows and equals 1.5. Comparing the two z-scores, we can see that the math exam has a higher value, suggesting that the student did better on the math exam than the Spanish exam when accounting for the difficulty of the exams. Located in the video script is a website where you can practice more problems with z-scores with solutions.